mistakes on, if I ask you to define something in the exam, epsilon delta definition, and you get one slight thing wrong, that can make the whole definition wrong. So it's very important to know your definitions in this course, and also to know the theorems and the proofs of the theorems that you're required to know. Okay, so if I say state and prove the monotone convergence theorem, that doesn't mean, oh, well, I'll state something and then I'll give a proof of something that's close to it because I can't remember quite well. No, it means you've got to do it exactly. Okay, so your statements have to be 100% correct to get 100% of the grade. So I can ask you to state and prove the monotone convergence theorem, or state and prove the extreme value theorem, or state and prove the mean value theorem. In addition, in an exam, if you have a sequence, say, that is decreasing, and you manage to show it's a lower bound, and I ask you, whether it converges or not, you would be better off not just saying yes or no. You'd be better off saying, yes, it converges by the monotone convergence theorem. So in other words, what I'm saying is, give evidence that you know where these things are coming from. State any theorems that you use to make a statement of fact. Okay? Is that clear? And that's written on the front of the exam. State any theorems that you don't prove when you use them. Okay, so I'm just going to go through a brief few-minute course summary. This just basically gives you a broad idea of what we did in this course. And then I'm going to do the practice final exams. And I'm also going to look at some of the assignment questions from assignments 1 through 4, especially assignment 4 since it wasn't handed in for grading. So, does this respond to anything? Yes. So let's just cut the course up into some broad pieces to make it easier to get an overall picture. We could say the first part of the course was all about the completeness axiom. And by that I mean the completeness axiom and everything that we did around the completeness axiom. So, the positivity axioms. Right? Those are very simple. Right? Positivity axioms, 1 is a positive number, and for any real number, either it's positive, 0, or negative. Those are the positivity axioms. The Archimedean principle, that's something that you need to know how to prove. Right? And that comes, again, what is the Archimedean principle? As I state and prove it, it says that for any real number c, there exists a natural number n bigger than c. That's the Archimedean principle. Okay? So you have to be able to state that and prove it. The proof is 5 lines, it's in your notes. Density of the rationals. Again, you have to be able to prove that. And that's on one of the practice finals, in fact. Show that the rationals are dense in the reals. And there are some ingredients to that you're not required to know. You can check that in your online topics that you have to know. You don't need to be able to show that from x to x plus 1, including x, there's an integer. Like that's some lemons and stuff that go into it. But you need to know how to give the proof of just the part of that is the density of the rationals. And I could ask you to prove the density of the irrationals as well. Right? Why are the irrationals dense? Well, because if you take the rationals and you multiply them all by square root of 2, you get irrationals. And so, shifting over by square root of 2, it's still dense, right? So we did that. We did that anyway. So you need to understand what this density means. What is density, right? You need to understand that. Then there's the completeness axiom. You need to be able to state it precisely, and you need to be able to use it to show that certain real numbers exist, like the square root of 2. And we've done many examples like that, and I'll do another one when we get to the practice finals. Inequalities. We had a couple of inequalities. We had the triangle inequality. You need to know the triangle inequality. Why do you need to know the triangle inequality? Well, because sometimes it comes up when you're doing the epsilon n or epsilon delta definition of limits. Right? You've got all these absolute values, and sometimes you want to say the absolute value of this plus this is less than the absolute value of that plus the absolute value of that. Okay? So you sometimes need to use the triangle inequality. There's also induction. We did a whole bunch of proofs by induction, so I could ask you to prove some statement by induction. Very important when you do induction to make it clear that you understand how mathematical induction works. So, a lot of you make mistakes on the assignments. For example, if you want to prove that the sum of the first n positive integers is n times n plus 1 over 2, right? That's one of the basic things that's in your notes. You have to say that we prove it for n equals 1, check it for n equals 1, that's the base case. And then you assume that the statement is true for some value of n, and you want to use that to prove that the same statement is true for the next value, n plus 1. And that's where a few people went wrong. What people did was they just wrote down, oh, well, here's the statement for n plus 1. And then you just simplify. You write down this equation and you simplify each side. Now, if you do that, you're not making it clear that you understand what induction is doing. You have to make it clear that you know that the statement for n is true, but you do not know that the statement for n plus 1 is true. That's what you're trying to prove. Okay? So you make that clear. Statement for n is this. We are required to prove, or required to prove, the statement for n plus 1. You can't use the statement for n plus 1 to prove the statement for n plus 1, because that's redundant. Okay? So make sure, and you check that, make sure, check the notes, check the book, that you know how to lay out a mathematical induction. And then we went on to limits. There's the epsilon capital N definition of the limit. Right? That is to define for a sequence an, the limit as n tends to infinity of an when it exists. So, given a sequence, you need to be able to show that the limit is some value. Recurrence equations. We didn't focus on solving them because in general you can't. What we focused on instead is finding their limits. So given an equation for an in terms of an minus 1, can you find the limit of an? Now remember, when you do that, you have to be a little bit careful. You have to first know that an has a limit before you actually find it. So given the recurrence, to find the limit, you just put some unknown value of the limit, call it a, into the occurrence, and you solve for recurrence, and you solve for a, right? You get some equation for a, and that tells you what the limit should be. But you can only do that if you know that that exists. And so, for occurrences, we wanted to have a method for showing that a limit exists, and the way we did that was the monotone convergence theorem. So if you have a question on recurrences, generally you'd be led through to say, okay, show that the sequence has a lower bound or an upper bound. Show that an is less than or equal to 1. That you have to prove. Next, show that an increases, for example. Show that an is less than or equal to an plus 1. That's saying that it's increasing. And once you've got those two things, I would then say, well, why does an have a limit? And that's where you should state the monotone convergence theorem. And once you know that, you could then be asked to find the limit. Okay. We did many examples like that. Please review those examples. Okay. Then there's, as we just said, the monotone convergence theorem. I could ask you to state and prove it. The Bolzano-Weierstrass theorem, same thing. I could ask you to state and prove it. Or I could ask you to state and prove a part of it. Right? What was the main part of the Bolzano-Weierstrass theorem? There was some main clever part of the proof. And then once you've got that part, there's just a few more lines. It's not much more to do. Do you remember the stuff with the peaks? Right? That's the main key idea in the proof of that theorem. So what did that say? That said that every sequence has a monotone subsequence. Right? So I could ask you to prove that. Related to that, I put this online because it's just an absolutely beautiful thing, but it's not required for the exam, and that is the Erdős-Szekeres theorem. So remember, we did this finite version of it. Like, I give you a sequence of length n squared, and you find in there a monotone sequence of length n plus 1. So remember that finite version of that theorem. That's not examinable, okay? But it is online if you like it. Okay, so the Bolzano-Weierstrass theorem, what does that say? That says that if you have a bounded sequence, then it has a convergent subsequence. Right? Why is that immediate once you've proved this thing with the peaks and the valleys? Well, it's immediate because of this theorem, right? You take your bounded sequence, it has a monotone subsequence. That was the peaks and valleys stuff. Now you know there's a monotone subsequence. The original sequence was bounded, so this monotone subsequence is also bounded. And so it has a limit. That's the monotone convergence theorem. Any questions about this? Right, so, again, important things. Being able to prove that the limit of a sequence is some value using epsilons and n's. Being able to prove that a recurrence equation has a limit and finding the limit. And being able to prove these two theorems. Okay. So that was for limits of sequences. And then we use that to define limits of functions. So this is from after the midterm onwards now. So there's now the epsilon delta definition of the limit of a function. The limit is x tends to a of f of x is L if and only if defined. You should be able to write this thing down precisely. Okay. And similarly, the definition of continuity, that's a little easier, right? What is the limit as x tends to a of f of x if f is continuous? It's f of a. And that's the definition of continuity. Right? So you can just put whatever x approaches, you can put that in the function. That's what continuity is. The extreme value theorem, I could ask you to state and prove it. Yeah, right. Well, it would be a bit much to ask you to state and prove the whole extreme value theorem, because it's a bit long. But I could ask you to prove some part of it. So make sure you understand those proofs. And when you learn proofs for this course, the proofs are not hard if you break them down. If you try to look at it as one big proof and try to understand the whole thing all in one part, that makes it hard. But even if you take the extreme value theorem, if you break it down into 3 or 4 parts, and what you're trying to do in each part, that makes it much easier to understand the whole thing. So that's what I would recommend. And then the intermediate value theorem. That's a theorem which is very applicable. You may be asked to use it to show that a certain equation has a root without the completeness axiom. So this is different. So how do we know that x squared equals 2 has a solution? From the intermediate value theorem, we'd say, well, if x is 1, it's 1. If x is 2, it's 4. X squared is continuous. So by the intermediate value theorem, there's a place between 1 and 4 where x squared is 2. So that's the intermediate value theorem. You must be able to use the intermediate value theorem to find values of functions. Uniform continuity, you must know the definition of that. And you must be able to show that uniform continuity implies continuity, for example. Uniform continuity, remember, is stronger than continuity. And then we did a little bit on limit points. All this is trying to find the limit of a function at a point that's on the edge of its domain. And that's what limit points